All right. Good morning, everybody. Welcome back. So today we will start the next chapter, which is chapter number 5. This is a very short chapter. However, it will require a lot of after class work to grasp well the concepts for chapter number 5. Okay, so let's start sharing my screen here with you. So chapter number 5, we will talk about properties of gases. Most of the chemical reagents and products are in the gas state at room temperature, and a lot of reactions, they produce a gas as the product. So therefore, it is important for us to understand the properties of gases. We will start with the gas laws. Then we will tackle gases produced in chemical reactions. So we will introduce a little bit of stoichiometry in the gas study. And then the last part of this chapter, we will talk about mixture of gases, kinetic molecular theory of gases, and also the real gas. Okay, very good. Okay, so let's start here with some observations to motivate us to study gases. If we fill two balloons, one with helium and one with CO2, for some reason, the balloon filled with helium will tend to go upwards, will float in the air, while the CO2 balloon will tend to go downwards and sink in the air. Okay, so one of our goals is to understand why we see this behavior. On a hot day, your tires have a higher chance of blowing up when compared to a cold day. This is related with the gas transformation, and the other goal for us is to understand why this happens. All right, so let's start talking about gases. The characteristic of gases are that this kind of physical state is compressible or can be compressed and immediately fill the space available to them. Okay, so remember that a gas does not have its own volume and it will fill up the space available to them. Okay, so the volume of the gas will be equal to the volume of the flask that contains the gas. The gas state, in the gas state, the molecules are widely separated and in chaotic motion. Okay, so gas state is characterized by chaotic motion of the molecules. All right, so to characterize a gas, we need to know three different things about the gas: pressure, volume, and temperature. Those are the things that we need to know to characterize the gas. Uh, if you want to use an analogy to characterize a person, for example, you need to know height, skin color, eye color, hair color, and those characteristics will distinguish each person. For gas, is the same idea. However, the characteristics that will distinguish each gas are pressure, volume, and temperature. Now let's talk about each of these characteristics that we need to know. Let's first start with pressure. The pressure results from the collisions of the gas molecules with the walls of the flask, okay? So you are going to imagine that we have small molecules of the gas moving all over the place, and at some point they will hit the walls of the flask, and this is going to create the pressure of the gas. The unit in the international system for pressure is Pascal, symbol PA. However, we have two usual units that show up a lot. The first one is atmospheres, symbol ATM. Conversion factor between atmospheres and Pascal, 1 atmosphere is equivalent to 1.01 times 10 to the 5 Pascal. And the second usual unit that shows up a lot is Torricelli, symbol is torr. Conversion factor between Pascal and Torricelli, 1.01 times 10 to the 5 Pascal, is equivalent to 760 Torricellis. Okay, now let's talk about volume. Very simple here. The volume of the gas is equals to the volume of the flask. Okay, so there is not much to talk here about volume. Unit for volume in the international system is the cubic meters. And we may also use the usual unit, which is liters, symbol capital L. Conversion factor between cubic meters and liters. 1 cubic meter is equals to 1 times 10 to the third liters. And the last one, temperature. The temperature of the gas is proportional to the speed of the molecules or the kinetic energy of the molecules. Faster the gas molecules move, higher is going to be the temperature, okay? So keep that analogy in mind. The temperature will be proportional to the speed of the molecules. Low temperature, low speed, high temperature, high speed that the molecules are moving throughout the flask. The unit that we are going to use for temperature in any case that we will study gases is Kelvin, and that's the international system unit, symbol for Kelvin, capital K. If we need to convert from Celsius to Kelvin, that is the equation that we are going to use. The temperature in Kelvin is equal to the temperature in Celsius plus 273. In the next slide, we are going to discuss when we are going to use each of the units that I showed you for pressure, volume, and temperature. Okay. Okay. So to make things simpler, what we are going to tackle here initially is the ideal gas. Okay, ideal gas is an idealized situation where everything is perfect and the system is the simplest system we can have. Okay, so we are always looking for the ideal situation to start with, because that will allow us to build the model, and then we can improve this model towards a more realistic concept. In an ideal gas, the intermolecular interactions and the volume of the molecules are neglected. Okay? So there is a special condition where the real gas behaves as an ideal gas, and this condition will translate to weak intermolecular interactions and neglected volume of the gases molecules. Let me switch to the other screen here really quick. Okay. The conditions of pressure and temperature where the real gas behaves as an ideal gas are low pressure, and high temperatures. The high temperature is needed because that will increase the speed that the molecules are moving in the flask. And because they are moving at a very high speed, there is no time for the molecules to interact with each other. Low pressure will translate usually in a large volume for the flask. If the volume of the flask is so high when compared with the volume of each molecule, we can say that the volume of each molecule is basically zero. The equation that correlates pressure, volume, and temperature is called ideal gas equation, or also called Clapeyron equation. And it states that pressure times volume equal to number of moles times the universal gas constant times temperature. Okay, so this equation will correlate the three principal characteristics of a gas: pressure, volume, and temperature. Let's take note of each of the parameters here in the equation. P stands for pressure. The units for pressure in the international system is Pascal, or we can also have a usual unit of atmospheres, symbol ATM. V in our equation stands for volume. Unit for volume in the international system is the cubic meters, or we can have also the usual unit liters. N stands for number of moles. The only unit possible for number of moles is mole. R, that's a very important member of the equation. And R is the, universal gas constant. Let me talk about temperature, and then I will get back to the universal gas constant to discuss the units. And T, finally, stands for temperature. The only unit possible for temperature in this equation is Kelvin. Okay? And that's the unit of the international system. So this equation will describe any state of any gas where we can say that the gas behaves as an ideal gas. And that's going to be basically 90% of our cases, okay? A very simple case, ideal gas behavior for most of the cases that we work with. The ideal gas equation will correlate pressure, volume, and temperature. And looking at the equation, pressure and volume, they may have different units that can be used. Number of moles and temperature always will have the same unit. So when do you know, for example, to use Pascal for pressure or atmosphere? The trick here is to look at the units of the universal gas constant, okay? So the international system unit for the gas constant will show up in joules, mole to the -1, Kelvin to the -1. Attention here, because joules can be decomposed in Pascal, cubic meters, and then we will have mole to the -1 and Kelvin to the -1. So looking at the units of the universal constant will give you the clue for the units of everything else in the equation, okay? So therefore, Pascal is going to be our unit of pressure, cubic meters, our unit of volume, mole, our unit of number of moles, and Kelvin is going to be the unit for temperature. Another possibility for the units of the universal gas constant is ATM, liters, mole to the minus 1, Kelvin to the minus 1. When the constant shows up in those units, ATM, liter, mole to the minus 1, and Kelvin to the minus 1, that means you must use pressure in atmospheres, volume in liters, mole is going to be our unit for number of moles, and Kelvin, the unit for temperature. Okay, so we will have to pay attention to the units of the universal gas constant to determine all the other units that are going to be used in the ideal gas equation. Two possibilities here: joules, mole to the minus 1, Kelvin to the minus 1, therefore all the international system units, or, for example, atmospheres, liter, mole to the minus 1, Kelvin to the minus 1. Therefore, we are going to use the usual units: pressure in atmospheres, volume in liters, mole, and Kelvin for number of moles and temperature, respectively. Okay, so remember, I'm going to repeat again. The ideal gas equation will describe any conditions or any state for an ideal gas. And here we are correlating the three main characteristics of a gas: pressure, volume, and temperature. Be very careful with the units. Okay? Take a look at the universal gas constant units to figure out the other units that are going to be used in the equation. Okay, so now that we know the ideal gas equation, let's do here a quick example to practice and try to understand how to use the ideal gas equation. A 1.5 liter flask contains 0.125 moles of CO2 at 27 degrees Celsius. What is the pressure assuming that CO2 behaves as an ideal gas? The universal gas constant has always to be given, and in this case is 0.0821 atmospheres, liters, mole to the minus 1, Kelvin to the minus 1. Okay, so I will give you about 2 minutes. Try to set up the problem. First, verify the units, and then we will solve it together. Okay, so let's set up this problem. So first thing here, we are going to look at the universal gas constant and its units to determine the other units that we have in the system, okay? So first here is going to be our unit of pressure, therefore ATM. In second is the unit for volume. Third is the unit for number of moles, mole, and the last here is the unit for temperature. Okay, so attention here, for number of moles and temperature, you just ignore the -1, okay? So we are just looking at the units and not the exponents. What we have here in this problem is a flask. The volume of this flask is 1.5 liters. This flask contains 0.125 mole of CO2, okay? In this case, is an ideal gas, so we are going to treat the CO2 as a very tiny little dots. The temperature that the CO2 is submitted to is 27 degrees. And remember that the gas moves all over the place. So the movement of the gas is random and eventually will hit the walls of the flask. And because the molecules hit the walls of the flask, that will cause pressure. And pressure is what we are looking for. Okay, so now that we have all the information given to us, let's double check the units. For volume, we must have in liters, so that's good. For number of moles, the only possible unit is mole, so that's good here. For temperature, we must have it in Kelvin. However, we have here in Celsius, therefore, we must transform Celsius to Kelvin. The conversion here is very simple. We are simply going to add 273. Therefore, the temperature in Kelvin is going to be 300 kelvins. And now the unit of temperature matches the unit in the constant, okay? We are always going to use the unit in Kelvin because the lowest temperature possible in Kelvin is 0. Therefore, that will avoid negative temperatures in the equation. Okay, so if we have volume, number of moles, temperature, and ideal gas constant, and what we are looking for is the pressure, and this gas behaves as an ideal gas, we can use the ideal gas equation. Pressure times volume equals to number of moles times ideal gas constant times temperature. Now let's replace everything we know in the equation. Pressure is what we are looking for. Volume of the flask is 1.5. Number of moles that we have is 0.125. Ideal gas constant that's given to us 0.0821. And, oops, finally temperature in Kelvin, 300. .5 is going to move to the other side doing the opposite operation, we are going to end up with pressure equals to 0.125 times 0.0821 times 300 divided by 1.5. Therefore, the pressure that this gas produces in these conditions is going to be equals to, according to my numbers here, 2.0 atmospheres, ATM. Okay, so careful here with the unit ATM that came here from the unit of the ideal gas constant. Okay, so always try to visualize the molecules inside the flask in a random motion. They will eventually collide with the walls of the flask, and that will cause the pressure of the gas. So let's think about one thing here. We know that at these conditions, the pressure is 2 atmospheres. What would happen if we increase the temperature of the gas, keeping the volume the same, the number of moles the same? So what would be the effect of increasing the temperature on the pressure of the gas? Would that increase the pressure, decrease the pressure, or have no effect? Let's think about that for a minute. You don't need to answer me, and then we can move on. Okay, so let's imagine this situation doing here an analogy. Imagine that I take all of you and lock inside a small room. And initially, I turn down the temperature. So therefore, you will randomly move around the room with low energy because it's cold. Some of you will not move at all. If I increase the temperature, now it becomes hotter. So there are a higher probability of you moving around with more intensity. So with the gas, the idea is the same. If I increase the temperature, I'm providing the gas with more energy that will result in higher speeds. Therefore, the probability of the gas to hit the walls of the flask increases. Therefore, it will result in increased pressure. Okay, so think about the concept before you start solving the exercise. This way, when you get the number, you will be able to judge if this number makes physical sense or not. Okay, so there's still time to start talking about transformations. If a person changes, for example, the hair color or the haircut or get a tan, so that will change one of the characteristics of this person. Therefore, we can say that this person went through a transformation. In a gas, the idea is the same. However, a gas transformation involves a change in the pressure and or volume and or temperature of a gas. Okay. We are going to look at pressure, volume, and temperature because those are the characteristics that define a gas. Therefore, a change in all of them or two of them define a gas transformation. In a gas transformation, we always have an initial state that's going to be disturbed to go to a final state. And we will change all of the characteristics of the gas or two of them. For simplifying our studies, we will only consider systems where the gas cannot escape, okay? Always closed systems. Because we are dealing with closed systems, the number of moles do not change. Okay, so closed systems means that the number of moles do not change. An example of a gas transformation is shown here. Imagine that we have a plastic bottle filled obviously with air, and we close this bottle. Air behaves as an ideal gas in this case. If we move this bottle from room temperature to an ice bath at 0 degrees, you will see that the bottle kind of shrinks because now it's colder, the gas is moving at lower speeds, and that decreases the pressure, causing the bottle to shrink. And therefore, we are changing one or more characteristics of the gas, and that will define a gas transformation. Okay, I want you to keep in mind that the ideal gas equation will describe one situation or one state of the gas. However, when we are transforming the gas, when we are moving from an initial state to a final state, in this case, we are having a transformation, and then a different equation will need to be used. For simplifying our studies, we will only work with closed systems, and in this case, the number of moles is constant, okay? Okay, so if the number of moles do not change, we can establish a correlation between the initial state and the final state. Okay. So the correlation between the initial state and the final state in a closed system is that the product pressure per volume divided by temperature has to be equal to the product pressure per volume over temperature for the final state. On the left side of the equation, we are looking at the initial system. And on the right side of the equation, we are looking at the final system. So every time you have a gas transformation in a closed system, PV over T must be equals to PV over T, initial state, initial system, and final system. And I'm going to stress this again. The temperature must be always in Kelvin. The reason for that is to avoid negative temperatures in the equation. For pressure and volume, when there is a transformation, we must have the same units on the left side and on the right side. Okay? Be very, very careful with the units. And again, every time we change two or more of the characteristics of the gas, that defines a gas transformation. Closed system means that the number of moles do not change during the transformation. Okay, so at this point, I think it is a good time for us to stop. Remember that this Friday we will have regular lectures, so we will meet here on Zoom at the regular time, and then we will move on with gas transformation and also probably talk about the kinetic model of a gas. Okay, so with that being said, I will finish for today at this point, and I will see you on Friday. Bye-bye.
Thank you, Professor.
Bye. Thank you.
Bye-bye.
Thank you.